Last time we were looking at the Feynman propagator, which was given by this expression. I think I did not write the expression yet, but we wrote this as theta of t prime minus t d of x prime minus x plus theta of t minus t prime d of x minus x prime. Okay, that's the expression for df, and we argued that df is a Lorentz invariant quantity. That's what we showed. And also let's remind ourselves that the expression for d of x prime minus x is the following. We wrote it as d4k over 2 pi 4 and then k square minus m square. Then we had a theta of k0 and e to the minus I k dot x prime minus x. Okay. And we argued that this is Lorentz invariant quantity, and please make sure that you are able to show that this is Lorentz invariant. And also you recall that this originally we wrote the expression for d x prime minus x as follows. So, it was d cube k over 2 pi cube. Okay, I realize that I have missed the factor of 2 pi here. It was d cube k over 2 pi cube 1 over 2 omega k times e to the minus I k dot x prime minus x. Okay, and of course, this is Lorentz invariant because this is, and I think I also showed that, or probably gave as an exercise to show that this is Lorentz invariant. Okay, remove this. So, this is where we stopped last time. Now, I want to look at some integral, okay, just for fun. And the integral which I want to look at is the following. So, I look at the integral d4 k over 2 pi to the 4 iota over I over k square minus m square e to the minus I k dot x prime minus x. Okay, let me give it a name. Okay, I have written x prime minus x because it's only a function of x prime minus x. It doesn't depend separately on x prime and x. It always comes as this combination. Now, if I look at this integral, and if I repeat the arguments that we were giving last time when we were analyzing this integral, okay, you see that this is a Lorentz invariant object. Okay, because the denominator is invariant, the measure is invariant, and this will be invariant if you appropriately change k to lambda k. Okay, if you are going from x prime minus x to lambda of x prime minus x, the same reasoning which we gave last time will work, and this is Lorentz invariant. Now, let us look at this a little more closely. I will write it as d cube k over 2 pi cube, and the limits are from minus infinity to plus infinity. And then we have the e to the I k dot x prime minus x, okay, and then we have the integral from minus infinity to plus infinity dk0, okay, and then I should write this one. This is iota over k0, doesn't matter, but let me write it like this, minus m square times e to the minus I k0 t prime minus t. Okay, so all I have done is just rearrange the terms. So this is same as the above. Now the integration is over the real line for k0 and also the k, but I can always look at it as an integration in the complex plane, and the contour of integration is over the real axis. Okay. So that's what I will do. So if I look at the k0 integral, the integrand has a pole or has poles at the place where the denominator goes to 0, right. So for any k, for every k, we have the following poles of k naught in k naught plane. And how do you get the poles? You get the poles by solving the denominator and equating it to 0. So you have k0 square minus this object, you remember this is just omega k. So you have minus omega k square. Okay, so this is how you will find the poles, and clearly the poles are located at k naught is equal to, let me write it here, k naught is equal to plus omega k, that is one place, and minus omega k. Okay. These are the location of the poles. So let us see. So here if I see, k0. So this is the way of denoting the complex plane in general. So that's the standard way of writing. So when I write k0 like this, I mean the complex plane of k naught. So here on this axis you have real k0, and here you have imaginary k0. Okay. Okay. So the integral is from minus infinity to plus infinity, which means the integral is over this real axis. Okay, I have to integrate over this line, and I have seen that there are two poles, and those two poles I will denote by crosses. Okay, so one is at here value minus omega k, and one is at omega k. Okay, so these are the two locations of the poles. Now having a pole is not a problem, but having a pole on the contour of integration is a problem, because your integral is not defined then. Okay, so the problem is with this integral, which I am right now looking at, is that it is not defined because the pole lies on the integration contour. So which is the situation here. So the problem is that the integral is not defined, and it is not defined because there are poles on the integration contour. Okay. Let us see why this integral is not defined if you have poles on the contour of integration. Let me give you a simple way to understand this. So let us forget that there are two poles. Let us take one pole on a contour of integration. So suppose I am looking at some integral over this contour, this real axis, okay, and you have a pole sitting on the contour. Okay. Now let me call it as integral I. Okay. Now what I will do is I will take the pole of the contour. Okay, so I, instead of looking at this object which I do not know how to calculate or what it means, I will look at the following object. I take this one. So, I take pole here. This is again my, as before, the integration contour. Okay. And what I will say is that I will let this pole approach here. Okay, and when it reaches the contour, that is the integral I am anyway interested in. So, this is the one I am looking at. Okay. Or equivalently, you can do the following: instead of taking the pole off and bringing it to the axis, we can indent it. Okay, so what we can do is we let the pole here, let it be there, and we change the integration contour. So, we come up to here and then we make a detour and we continue like this. Okay. And then you take the semicircle to go to 0, and then you get a result, and you would try to interpret that it is providing a continuation to this this integral. But then you also have a possibility of doing this. The same thing, you leave it here, the pole is there, and you integrate along this path. So, you come up to here from minus infinity, and here you make a small detour and continue like this, and then again take the semicircle to go to 0. Okay. In that case, you will be really in this situation. Okay. Now, let me write the integral in this case, this integral. Okay. So, this is not this one, this is different. Okay. So, this integral let me call as I minus is equal to I p. So, I p is from minus infinity to here and then here to infinity, plus I of gamma, okay, and this semicircle I am calling gamma. And similarly, this one I will call I plus the whole integral, and then the integral from here to here and then from here to here I will call as I p, is the same as above, plus this part, okay, and I will call it I gamma prime. Okay. Now, let us see if I prime and I give the same answer. If they do give the same answer, then I should get I minus I plus is equal to 0, and this is what I should expect, right, if I minus and I plus are same. And I could say that this is what I minus and I plus are giving the result for this integral. This is how I could define it. Now, let us see what we get. When I calculate this, I get I minus I plus is equal to the I p, the principal part is same in both. So, that drops out, and I get I gamma minus I gamma prime. And what is I gamma? I gamma is this integral. Okay. So, it is basically this integral, and the direction is this, minus what is this one? This is this one. Okay, which is same as this plus the minus sign I can absorb and change the direction of the sense of the contour. So, it will become this, and it was this here, which is same as having this is the first term is going to give you this one, and the second term when you add it gives you this, and the pole is there. Okay. And this is when you do the integral, this is 2 pi I times the residue of the pole which is lying here. Okay. So, you see that I prime, I minus and I plus they differ by 2 pi I times the residue of the pole. So, you do not get 0. So, you do not get the same thing. So, there is an ambiguity. You cannot just say that I will take the limit of I minus and take the limit in which the semicircle goes to 0, and I will say that this is what defines this integral, because you see that you also have another possibility and which is giving you a different result, and the result is the residue of the pole there times 2 pi I. Okay. So, we see that if you have a pole on the integration contour, that is not defined, as I have shown you here. So, which means the integral with which I wanted to play for a while is not a defined integral. So, I will now then play with another integral. So, now I will look at a different integral. So, let me look at this one, d4 k over 2 pi to the 4 I over k square minus m square, this and e to the minus I k dot x prime minus x. This was not defined. So, what I will do is I will put a plus I epsilon here, where epsilon is positive. Okay, it is a real number, I need a real quantity, okay, and it is vanishingly small. Okay, so, it is very small, and let us see whether this integral is defined or not, whether we still have poles on the integration contour, and of course, we do not have because of this I epsilon. Okay, so, again our integration contours are from minus infinity to plus infinity for all the 4 variables, and let us look at where the poles are located in the k0 plane. So, what we want to look at the poles of k0. Okay. So, what I want to do is k square minus m square is basically k0 square minus omega k square, as you saw before, and you have a plus I epsilon, and let us find out where this becomes 0. So, I will give you the solution, it is easy to find out. The solution is k0 is omega k minus I epsilon, that is solution number 1, and the other solution is minus omega k plus I epsilon. So, these are the 2 solutions. Okay. I think this is correct. Now, let us see whether this is correct. All I will do is take k0 minus first solution and then the second one, k0 minus the second solution. Okay. So, this is k0 square, and then you get a, when you multiply this piece with the k0, you get minus k0 minus omega k plus I epsilon. Then you multiply this and this, you get minus k0 omega k minus I epsilon, and then when you multiply, so this is, these are this, and then you finally multiply the 2 terms here, you get minus into minus is plus and omega k minus I epsilon into omega k plus I epsilon. Okay. Now, let us see k0 omega k with the plus sign, k0 omega k with the minus sign. So, these 2 cancel. This is minus k0 I epsilon, this is minus, no, plus k0 I epsilon. So, this term also goes away, and we are left with k 0 square somewhere it has, yeah, this one I forgot to sign, and this one gives, this times this is minus omega k square, and then you have minus I epsilon times minus omega k gives you I epsilon omega k. Sorry, I should use the same symbol. And when this one multiplies, it also gives you I epsilon omega k. So, you have 2 I epsilon omega k, and then this one gives you I times I is minus 1 minus minus plus epsilon square. Okay. But we are taking epsilon to be vanishing small. Now, if epsilon is vanishingly small, 2 times epsilon is also vanishingly small. So, I can just, instead of writing 2 epsilon, I can just write the same thing as epsilon, okay, just because epsilon is small. I am not interested in the value of epsilon, I just want it to be something very small. Okay. So, this object then becomes k 0 square minus omega k square 2 I epsilon omega k. I can write it the same thing as I epsilon omega k is also absorbed there. If I can absorb 2, I can absorb omega k also, and I drop the epsilon square term because it is 1 order higher in smallness. Okay, so, you see that this is exactly what we started with. So, clearly these two are the solutions. So, these two are the solutions, that is what I have shown. So, let us see where the poles are in the k naught plane. The poles are here. So, one is at omega k minus I epsilon. So, minus I epsilon means it has a negative imaginary part. So, it is here, and you have minus omega k plus I epsilon. So, there is a positive imaginary part. Okay. So, here, so one is minus omega k plus I epsilon, and this is omega k minus I epsilon. Okay. So, at least the integral appears to be well defined because there is no pole lying on the integration contour. Okay. So, this is good. So, unlike the previous one, this one is nice, and now that we have come so far, let us do the integral over k naught. Okay. So, I will do one integral. Okay, let us do that. Yeah. So, let us go to the next page. So, I have dk 0 I over, and of course, d cube k is also there, and all the factors of 2 pi k 0 square minus omega k square plus I epsilon, right, and e to the minus I k dot minus x, and the situation is this. You have a pole here omega k minus epsilon, and then you have a pole there omega k plus I epsilon, and what is the integration contour for k naught? It is the real axis, right. This is where you have to do the integral. This is from minus infinity to plus infinity. Okay. But now I can do the integral. Okay. Now, it would be nice if I could close the contour, because if I could close the contour, let us say like this, okay, and then take the limit where the radius of this semicircle goes to infinity. In that infinite limit, I will have a the contour will be from minus infinity to plus infinity and a infinite semicircle closing it. But I can do so without the changing the value of the integral only if the contribution that I get from the semicircle is 0, right. Because if the contribution from the semicircle is 0, I can add it to my integral, right. And the advantage would be that then the result you can easily get using Cauchy's theorem, and all you have to do is just find out the value of the residue at this pole and multiply it by 2 pi I. Okay. But now whether you should close it like this or you should close it below in the lower half plane, how do you decide that? So, there are two issues. How do I decide which way to close, and second, whether I can really close it, because I have to ensure that the value of the integral from these semicircles, these infinite semicircles is 0, right. So, let me make it let me repeat what I am trying to say. I am saying that the integral over this real axis I have drawn here, the integral over this is same as integral over this plus integral over the semicircle, provided the contribution you get from the semicircle is 0. If it is not 0, then you cannot write these two as same, right. If contribution from this infinite semicircle, infinite meaning infinite radius, vanishes. Okay. So, let us see what I will do is, first I wish I had not drawn this, but anyway, okay. So, first let us consider a situation where t prime is greater than t, okay, or t prime minus t is greater than 0, same thing. Let us look at this situation. Then the k0 integral is the following. You have integral dk0 over 2 pi, okay, I over k's, what were the, these are the poles. So, you have k naught minus omega k plus I epsilon times k naught minus, sorry, here I should have put a minus. So, there is a minus, and then you have a minus omega k minus I epsilon, okay. And then on the top of it you have e to the minus I k 0 t prime minus t, and then you have e to the I k dot x prime minus x, and then you have d cube k over 2 pi cube. Okay, so I have written down everything now, looks correct. Okay. Now, recall okay. Now, because we are taking t prime minus t to be greater than 0, let me just see in the notes. So, now what I want to do is I want to use Jordan's lemma. Okay. So, you will recall that if you have an integral over a semicircle and it is f dz f of z f of z e to the minus I alpha z dz, okay, where alpha is a real number and positive. Okay. Yeah. Then and where the semicircle is in the lower half plane. Lower half plane. So, you are closing the contour in the lower half plane, okay, like this. Okay. Then if your the function f of z vanishes fast enough, okay, as like 1 over mod of z, then this integral is gives you 0. Okay. So, this integral vanishes if alpha is greater than 0 and you close the contour in the lower half plane. Okay, that is important. If this is the integral given to you, you cannot close the contour in the upper half plane, that will not work. So, that will not vanish. Okay. And this is what is very useful for us, because look at the situation here. Instead of z, the what we have is k 0. Okay, we are in the complex plane of k 0, and t prime minus t is what is alpha here, which is positive. So, if alpha is positive, you have e to the minus k naught times whatever here, and the function of z here, you can see that this goes faster as 1 over mod of k naught, actually it goes as 1 over k naught square. Then this integral over k naught is going to vanish over the semicircle in the lower half plane, if you take that semicircle to be of infinite radius, okay, which I can put as limit r going to infinity, where CR is the semicircle of radius r. Okay. So, I will use this, and already it is clear what I should, already we have answered our both the questions, where I should close, whether upper half plane or lower half plane, and whether the integration over the semicircle is 0. So, I should close in the lower half plane for t prime minus t to be when t prime minus t is positive, and yes, the integral vanishes, as you can see from the Jordan's lemma. Okay. So, what I have here is that the integral which was, let me go to the next page. Okay, this is bright. So, let me write. Okay, just a second. Okay. You see, what we wanted to look at was an integral over k naught, okay, and it was on the real axis. Now, I have shown that if t prime is greater than t, then I can close the contour in the lower half plane, because the contribution vanishes, and this integral is same as this integral. Okay. And when I do so, remember there were two poles, one pole was there, one pole is here, and I pick up this one, and the result will be what? 2 pi I times the residue of the pole here. So, let us find out what is the residue. So, 2 pi I times the residue. Now, note that the contour is in the clockwise sense, clockwise direction, which is negative sense. So, I will get a minus sign. Okay. So, let me put that minus sign already here. Now, we want to look at the residue, and residue is what? Oh, I have moved 2 pages anyway. So, what is the residue? I should put, so this one is the piece which is giving the pole. So, I should put in the k naught here omega k minus I epsilon. So, if I do that, I will get omega, oops, I will get, let me write, say omega k minus I epsilon, and then you have minus minus plus, so another omega k. So, 2 omega k's and again a minus I epsilon. So, you get again a minus I epsilon. So, you get 2 omega k minus I epsilon. Okay. So, you get 1 over 2 omega k but you still have the exponential factor. This anyway does not get. So, here you will get e to the minus I, and the we were looking at omega k. So, you get e to the minus I omega k t prime minus t. Okay. So, what do I have then? I have not this. If I write the full integral, I had d cube k over 2 pi cube. Remember that? And then you have, let me see if I am making any sign mistakes. Yeah, I am making not that of a sign mistake, but I am missing that factor of I and this factor of 2 pi. So, that I is here, and we also have a 1 over 2 pi. Okay. So, I have d cube k over 2 pi cube, and then I into I is minus 1 minus minus plus, and 2 pi cancels. So, I have 1 over 2 omega k, and I can leave out the minus I epsilon, e to the minus I omega k t prime minus t, and remember that we have to take t prime minus t to be positive. Does that sound familiar? We have seen that before. This was exactly, no, I have again missed factor, plus you still have the k dot x prime minus x. This factor I should bring from here, and of course, there is a sign mistake here. This is the correct one. Okay, and this is the familiar result, and this is exactly what you had for df t prime minus t. Okay. And because this is only the result when t prime minus t is greater than 0. Okay, so that's good. Now, let us look at the situation where t prime is less than t, which is t prime minus t is less than 0. Then the Jordan's lemma tells you that you have to close in the upper half plane, okay, because the sign of alpha, which is t prime minus t, is negative now. So, you should be closing here. The sense of the contour is positive. So, I will, this minus sign will not appear, and I will have the following. Again 2 pi I times the residue, and residue is I over, let us go back here. Now, the look at this, we are going to pick up this pole, right, this one. So, pole is here. So, let us see what is the residue. Oops. So, this one is the one which is giving pole and this one is the one which will give you residue. So, you k naught will you put minus omega k and minus omega k from here gives you minus 2 omega k, okay. And this one, okay, let us come in. So, minus 2 omega k, the sense is positive, and let us look at the exponential factor. It was minus omega k, so get plus I omega k t prime minus t, okay. And then of course, you have the factor of 2 pi coming from the from here, this 2 pi, and the factor of I, which I already have taken. So, my result of the integral is integral d cube k over 2 pi cube, and then I substitute all this. I square gives you a minus 1, okay, and then there is a minus sign here, so which cancels and you get 1 over 2 omega k, and this is e to the minus I omega k t minus t prime minus, and I should bring that piece, and x prime x minus x prime, okay. So, I have brought that piece also here, and this you remember that this is d, not df, this is d of t minus t prime, and t is greater than t prime, okay. Which means that the integral I am looking at, this integral which I was interested in calculating, this is the following. Did I call it something? I should have given it a name, but it is okay. Let me write it down. So, integral d4 k over 2 pi 4 I over k square minus m square plus I epsilon e to the minus I k dot x prime minus x is equal to, that is equal to d of, not t prime minus t, I should write x prime minus x, okay, and this one should be x minus x prime. This is d of x prime minus x, but only when t prime is greater than t, which means I put a theta of t prime minus t, and plus if t prime is less than t, then this one should be the result. So, I can ensure that by putting theta of t minus t prime d of x minus x prime, and this is a familiar result to us, which means, and you recall that this is just the propagator. Okay, so, what we have shown is that this integral, which for curiosity we started looking at, okay, it exactly turns out to be the Feynman propagator. So, what I have shown is that df x prime minus x, or maybe let me do it a bit nicely. I have shown that the Feynman propagator is the following: df x prime minus x is integral d4 k over 2 pi to the 4 I over k square minus m square plus I epsilon times e to the minus I k dot x prime minus x. Okay. And what the I epsilon is doing is just telling you exactly how you have to close the contour, okay, and as I have explained here. Okay, so, we will stop at this point and we will continue the discussion further in the next video.